Okay, so the final exam for our class. So this is for section 3. The room number will be slightly different if you're in one of the other sections. But it's Thursday. It's in the evening of December 13th. And it's 8 p.m. to 10 p.m. And the room, it's in the what's called BCC, or the Business College Complex, in the business school. And the room is N100. Okay? Questions about that? So this is my first, as you know, this is my first time teaching this particular class. So I learned the exact format of your exam just a couple days ago. So it's 2 hours. Usually your quizzes are, well, I'm saying usually. Your quizzes are always 15 minutes long. Standard format. And so with 2 hours, you have slightly more than twice. So it's actually not going to be 20 questions. It will actually be 25. However, there's good news on top of that. We're only going to grade 21 out of 25. So you can miss 4 without 3. That's what I told you is how it works here. So I'm just going with how it works. Okay? I believe it's cut off. Yeah.
So if you get more than 21 right, you don't get more than 100.
Yeah, so if you get it come to the exam and you know the first 21 problems and you're sure you got them right, you just walk out. So I don't recommend doing that.
So it's not that you're not grading for a specific question?
No. It's okay. You can call them your 21 best answers. So since it's multiple choice, it's either wrong or right. And so you just throw away 4 wrong answers. Okay, that does not mean that the exam is easy. It can still be devilishly hard. So I still want you to prepare like it's difficult. It's the percentage of Bruno Silva's. I think I know, but if I say it and I get it wrong, everybody can write, so I'm not going to say it. Okay. Let's make that sound. Okay, so today we are talking about waves again. So if you didn't watch the class last time, or didn't see the video, we're talking about waves. This is kind of like a high school art project. I don't know. Did you see this last time? No. Okay, so here's the whole idea. You have a wave, basically it's a sine wave that's moving, and if I move it, you can notice how this thing just goes up and down. Okay? See that? I'll show you. It's very low tax. This is what the thing they did in the 19th century. Okay, that's kind of what we're doing. This function just strips over, but any given point it just goes up and down, and that's what it is. All right, so we already introduced waves last time, so if you didn't see the lecture last time, it's up on YouTube as usual, so you can go back and look at that. What we're going to talk about today is specifically what are called transverse waves. Okay? Transverse means perpendicular to. And so these are waves where the displacement is perpendicular to the wave direction of motion. Okay, so the prototype is you have waves on a string. So I don't have any elastic string here. I spent like 10 minutes back there trying to find string. But we'll have more demos later. So, you know, well, this is why that won't work too well. Take this so you can see. So basically, you have oscillations on a string like you have oscillations on something like this, where the displacement is perpendicular to the wave, perpendicular to the direction that the wave moves. So it's up and down, whereas the wave is moving in this direction, that direction. Okay? Everybody understand? Okay. So this is the day of low tech demos. So think of waves on a string. Okay, so we have a nice wave like this, sinusoidal wave, and these points are going up and down, and this displacement up and down is perpendicular to the wave velocity, which is, let's say it's going in this direction. Okay. Questions about this? Now, let me give you some information about what the speed of the wave will be on a string. So, for a string, of is not the word I wanted. A string with tension. So usually for tension we write capital T. However, capital T is used for period. And since we're talking about waves, this is very confusing. Your book uses something like T sub S for tension of the string. I find it a little easier to remember if I just write it as F sub T. It's the force, that's the tension of the string. Okay? It's a little easier to remember it's actually tension, it's a force. So your book writes it, I think, TS, T sub S, I'll just write F sub T. And something called the mass per unit length, mu. Okay? So what does this mean? If I'm going to calculate the mass per unit length, mu, so this is, right, what is mu? Mu is it's a Greek letter, lowercase Greek letter. It's sort of the analog of the letter M. If you write it as a lowercase letter, it looks like that. It looks more like a U than like an M, but it's just the way it is. Okay. So this mass per unit length, what you do is you take the mass of the string. This is the total mass. And then you divide by the length of the string. And that's how, obviously, you get the mass per unit length. Okay? That's all it is. It's the ratio of the two. So, we have a tension Ft and mass per unit length mu. This wave speed, this is a continuation of the same sentence, so lowercase the. The wave speed is v, let me just write string so that you remember we're talking about strings. It's the square root of Ft divided by mu. Okay. Questions about that? You can check that this has units, as you would expect, of meters per second. It has the right units. The tension is in units of newtons, which is kilograms times meters per second squared. And now the mass per unit length has units of kilograms per meter. So the kilograms go away, they get cancelled out. There's a meters in the numerator, but then there's a meters in the denominator of the denominator, which is the numerator. So you get meters squared, and then you have over second squared, you take the square root, it comes out right, meters per second. Okay? So what this means is that if you have more tension in the string, the wave goes faster. Okay? As you can see, it's proportional to the square root of the tension. If the string is heavier, if it has more mass, then it will be slower, which maybe makes some sense to you if you ever plucked a string. Or you may know, for example, so how many of you have played a stringed instrument of some sort? Yeah, good. A lot of people. So you probably know, like on piano, the low, right? There's different thicknesses. So the low strings, right, are very, very thick, have a lot of mass per unit length. The high strings have very little mass per unit length. And so they're adjusting the wave speed with this mass per unit length. Any questions about this? And obviously you can adjust the wave speed also with the tension of the string. Okay, let's go on. The next kind of wave we're going to talk about are longitudinal waves, which is the other type. So the longitudinal. And so these are waves where the displacement is parallel, or technically, or opposite. So we use the term parallel sort of loosely here, where the displacement is parallel or opposite to the wave motion. Maybe I should make this a complete, I'll make this a complete sentence. This is sort of a sentence fragment. Okay, I'll make this a complete sentence. Waves where the displacement is parallel or opposite to the wave motion are called longitudinal waves. Okay, so if you want a prototype to visualize, you can think of air in sound waves. Or a compressed string. Okay. Let's just talk about sound. So, I don't know if you really thought much about this, but sound, the reason that you can actually hear me is because first there's sound coming out of the speakers, wherever they are located, the ones closest to you. And you can hear my voice because the speakers are vibrating, and they're hitting the air molecules. And then the air molecules are colliding with each other, and so they collide and they bang into each other and form these waves, which are traveling through the air. And they're longitudinal waves. And they're a lot like if I had, you can imagine I have this coiled spring here, and I pulled it like this, and I just jerked a little bit, then you could have a little pulse of this compressed spring coming towards you. That's a lot like what happens with sound. Okay. So let me draw it from the side. So let's just visualize waves on a spring. And so let's start off with a relaxed spring. And let's just draw it like this. Use some relaxed spring like this. Okay, now let's say I have now a wave. This is not going to be a relaxed spring, but instead I will have, let's say, a region where it's stretched. And then I have a region where it's compressed. And then it's stretched and it's compressed. All right, so here it's compressed. Here it's also compressed. And here it's stretched. Here it's also stretched. Okay, now if you wanted to try to figure out which way the displacement is actually going, you can go to a particular point on the spring, and you can say whether that point on the spring moved to the right or moved to the right or to the left. Okay, so you could say, well, if this guy's stretched, if I'm on this side, let's say I'm let's see, my drawing is not exactly the same as my notes, so I should line this up exactly right. So here, let me draw the displacement. Okay, so if this guy's stretched, then on this side over here, the displacement's a bit to the right. Does everybody understand that? In order for that spring to stretch out, the point here had to move from, let's say, here to there. And then, however, a point over here would have to move to the left. Does that make sense? Maybe the easiest way to think about it is in order to compress this region here, these guys have to move to the right, and these guys have to move to the left. Does that make sense? Maybe that's a little easier to think about. Okay, similarly over here, I have to pinch. This guy has to go to the right, this has to go to the left. Okay, any questions about that? Okay, now let's talk about the speed of sound in air. The speed of sound in air is approximately 330 or 40 meters per second. It depends on the temperature of the air. It actually depends on a lot of things, like the pressure as well, but most often it's the temperature that changes. As we know, winter to summer is quite different in temperature. So the speed of sound in air at 0 degrees Celsius, the speed of sound in air is about 331 meters per second. If you are at 20 degrees Celsius, more like room temperature here, the speed of sound goes up to about 343 meters per second. If you want a way to estimate what it is at other temperatures, if you're not too far away from these values, there's a simple formula that, well, okay, I lied, it's not that simple. There's a formula you can use. The sound in air is equal to 331 meters per second, this value for the temperature 0 degrees, and then you take the square root of, it looks kind of funny, it's the temperature in Celsius, degrees Celsius. Now, we have not done temperature in this class, so I'm just relying on the fact that you probably wake up every morning and you look at the forecast, you look at the thermometer, and you know the Celsius scale. At least you know Fahrenheit, you've seen Celsius. Okay, so temperature in Celsius, that if you're 0 Celsius, that's when water freezes. But there's another unit called kelvins, and the formula is simpler in kelvins. And the way you go from Celsius to kelvins, once again, we're not doing any of this stuff in this class, but what you do is you add 273. The reason is kelvins is exactly the same temperature scale as Celsius, except for there's this thing called absolute zero temperature, which is negative 273 degrees Celsius. And we call that 0 Kelvin because if it's called absolute zero, why don't you make that 0 temperature? So go from Celsius to Kelvin, you just add the number 273. Anyways, if you want to get the formula, it's actually the temperature in Celsius plus 273 to convert it to kelvins, and then divide by 273. If you plug in this for 20 degrees Celsius, you get the square root of 293 over 273, and it comes out to about 343. Okay. Any questions about this? This is not that important. I'm just trying to give you a feeling for how it changes with temperature. Okay, let's do an example together. Let's say a string is pulled to tension 10 newtons and is, let's say 10 again, 10 meters long with mass equal to 4.0 grams. Okay, you can ask the question, what is the period of a wave on the string with wavelength 0.20 meters. Okay, so this is one of these problems where I'm combining your new knowledge with something you learned last time. Okay, let's start off with what we know about the string. We know the tension is 10 newtons. It's 10 meters long. It has a mass of 4.0 grams. So I know to get the wave speed, I have to do something that involves the mass per unit length. So mu, that funny symbol, the U with the little tail in the beginning. Okay, so that is going to be the mass of the string divided by the length. Okay, let's do that. So let's convert it to standard units. Remember, grams is not the standard unit, but it's rather kilograms. And so we would have 4.0 times 10 to the negative 3 kilograms. And now we're going to divide by the length. That's 10 meters. And that comes out to 4.0 times 10 to the 4th, 10 to the negative 4th kilograms over meters. Okay, let's keep going. All right. With knowing the mass per unit length and knowing the tension, I can calculate the speed of the wave. I know that's not what we asked for, but I'm pretty sure that's going to be useful. So this V string is the wave speed of the string. That's equal to the formula we just introduced. It's the square root of, by the way, we didn't derive this formula at all. My apologies there, but this is actually this is a rather complicated derivation to actually derive this. It's the square root of the tension over mu, mass per unit length. And so we have 10 newtons for the tension. We have the mass per unit length. We just calculated it's 4 times 10 to the negative 4 kilograms per meter. Okay, and we divide them and take the square root, and we get 158 meters per second. Now, if we have the wave speed and we know the wavelength, we can then figure out the period. So we know that V, let's say for the string, that's the wave speed. We had a formula that involves the wavelength and the period. And the way I remember what the formula was is V has units of meters per second. The wavelength has units of meters, so I need meters, so I need lambda in the numerator. And the period, capital T, has units of seconds, so I need that in the denominator to get the units right. So that's the formula, lambda over T. So, but we actually want this, the period T. So remember this guy's the period. This is the wavelength. Okay, so the period is going to be I can just cross multiply and then divide by v string, and that will give me a lambda divided by v string. And so that comes out to 0.20 for the wavelength divided by 158 meters per second. And that comes out to 1.27 times 10 to the negative 3 seconds. Probably I should chop this off to 1.3 times 10 to the negative 3 seconds, which is significant. Okay, any questions about this? Make sense? Okay. All right, the next topic we're going to cover is talking about the phase of a wave. And this is to set up something we'll actually do more about next week. So, the phase of a wave. Let's talk about that. Let's just continue on here. Okay, so we've been writing down formulas like the displacement, capital D. It's the amplitude times the sine function. And we remember we wrote it 3 different ways. The simplest way was something k times x. Remember, k is what we call the wave number, or the angular wave number, technically. And then we have omega. This was the angular frequency. So kx minus omega t. And then we said in general we could have this phase constant phi 0. But the thing I want to focus on is this thing here, this guy. This thing is called the phase. That's the phase of the wave. So the thing that's inside the sine function, the part inside the sine function, is the phase of the wave. So just kx minus omega t plus phi 0. Whatever's there is the phase of the wave. Yeah. Okay, so the wave number, that's something we covered a bit. Let me review that from last time. So the wave number is like, sorry, you can't see that. So let me back up and remember the angular frequency. Okay, so the angular frequency, this guy, I like to think it has units of radians per second, right? So how many radians it does per second, okay? So the analog of omega, radians per second, is the wave number, going from time to position, okay? So let me try to make this connection. So omega, there's a formula. Omega is 2 pi over t, where t is a period. Okay? So the period is how long it takes for a wave to repeat itself. Now, if I have what's called the wave number, I do 2 pi divided by lambda, the wavelength. So the wavelength is how long in space I have to go before the wave repeats itself. So if I do the same thing, 2 pi divided by lambda, that's the wave number. So the wave number is sort of how wiggly the wave is as you move from one point to another. If it's like this, then the wave number is very large. Okay?
So that radians per meter.
Yeah, radians per meter, exactly. Okay. So the units are radians per meter. Okay. Any other questions? Okay, so coming back to the phase of the wave is just whatever is there, okay, inside. So we wrote down kx minus omega t plus phi 0. That's the phase of the wave. Now let's specialize to a particular case. So if we compare, now we're going to compare the phase of the wave at 2 different values of x. Okay, if we compare the phase at positions x1 and x2, at the same time t, the difference in phase is, okay, we'll just write down the formula. So I take one point, let's say x1, and then I take another point x2, and I ask what is the difference in the phases between these guys. Okay, so for x1, I just get k x1 minus omega t plus phi 0. Okay, and I'm going to take the difference, and then I'm going to subtract the phase I get at x2. Okay, but at the same time. If you're wondering why I care about this, it'll come up next week. We're going to talk about interference, where we have two waves on top of each other, and we want to know whether they add up or they subtract or they cancel each other, called constructive and destructive interference. This will come next time. Actually, it'll come tomorrow in tomorrow's lecture. Okay, so if I subtract these two, that's what's called the difference in the phase, or the phase difference. So then we get the phase difference. Let me write it. Let's try to simplify it. Phase difference is, okay, all this stuff can be canceled because they're on both sides and they're exactly the same. So I end up with k x1 minus k x2, or if you want to clean it up a bit, I can write it as k times x1 minus x2. So sometimes there are special cases when the phase difference ends up being 0. If you're at the same point, x1 and x2 are at the same point, then we say they're in phase, they're at the same phase. But they also have the same phase if the difference between x1 and x2, well, we'll do this more next time, but suppose x1 and x2 was lambda, the wavelength, okay? Then if this is the wavelength, if I go back to here that the wave number is 2 pi over lambda, if I have 2 pi over lambda times x1 minus x2, which I'm saying is also lambda, then the lambdas cancel, and then this becomes 2 pi. And so 2 pi radians is again, it's like 0. 2 pi radians is going back to the full circle. Okay? So that would also be in phase. So we'll talk more about that next time. These are examples of constructive interference. But, any questions about that? Okay. The next topic we're going to cover is what's called the Doppler effect. How many of you have heard of the Doppler effect? Okay. Very good. So if you have not heard of the Doppler effect, probably all of you have heard an ambulance siren. And when it's coming towards you, you hear the pitch is higher. And then when it passes you, it sort of dies down, the pitch gets lower. Have you noticed that? Okay. Other examples are train whistles. When a train has its whistle coming towards you, it's also a bit higher when it goes away. It goes down. Actually, if you were in some other countries, like in some of the European countries, the actual ambulance sirens are these two-tone sirens. It's not quite as annoying as, well, they're still annoying, but not quite as annoying as the US. And you can really hear it because it really does change quite a lot. Okay. So this is an example of the Doppler effect. It actually happens for light as well, but we haven't been discussing light. We're just discussing sound here. Yeah, that's right. So the Doppler effect, so what is this? The Doppler effect is the phenomenon that a moving observer, what is a moving observer? It's, okay, moving is obvious, somebody's moving. The observer is somebody that's listening. The listener, moving observer, and or moving sound source, whatever is making the sound, creates the effect of a higher or lower. I know I'm sort of covering all possibilities in one sentence here. Higher or lower frequency. Okay, and I should mention the frequency of a sound wave is what we hear as the pitch. Okay. So, for example, those of you who do some music, you may know there's a note, like middle C on the piano. Sort of when you stand halfway in between, there's this key called middle C. And then there's a key called A, which the orchestra typically tunes according to. And that has exactly 440 hertz. In fact, it's defined that way. And so pitch is the same thing as frequency for sound. Now, the reason why the Doppler effect works is that if you have, let's say we have a source, here's my sound source, and let's say it has some speed Vs, and this is the observer over here. But because it's moved, okay, so I'm going to draw sort of concentric circles representing points with the same phase going out from the source, okay, like ripples on a pond. You throw, if you throw a pebble in, you see these concentric circles. These are waves on the surface. You can think of sound waves similar like that. But because the source is moving, the waves that were created long ago started from here, whereas the waves that are created later start from more over here. So as a result, it looks something like this. The ones that are older, that are bigger in size, are centered somewhat over here, and the ones that are newer are shifted more a little bit like this. Does that make sense what I'm drawing here? And so because these are closer together, I'm exaggerating a bit here, the sound, the observer just listening over here, the frequency sounds higher because it's coming closer to, it's moving towards the observer. Does that make sense? Kind of? Okay. You can also have, so this is the case where the source is moving. You can also have the case where the source is stationary, it's not moving. So then in that case, we have nice concentric circles. Sorry, I'm overlapping my circles here. I didn't mean to do that. Okay. And then let's say I have an observer here. And the observer is moving towards, let's say, VO for the observer. The observer is moving towards the source. Now, because the observer is moving towards the observer, we're actually piercing through these little ripples faster. So we hear the oscillations faster. Does that make sense? Okay. Because we're actually slicing through. Yeah. Yeah, exactly. Like a more compressed way. Exactly. Good. Okay. So the frequency again, in this case, the frequency sounds higher to the observer. So I've shown you the two cases where the source comes closer to the observer or the observer comes closer to the source. If we go in the opposite directions, if the source is moving away from the observer, the frequency sounds lower. Similarly, if the observer is moving away from the source, the frequency sounds lower in that case as well. Any questions about this? Okay, so let me then, I will give you the formula for, your book does this in so many pieces, it's kind of messy how they do it. I'll give you one formula for all of the cases, okay? The formula is the following. Okay, so I'll write this as F prime. That's the frequency heard by the observer. Okay. What's heard by the person that's listening? F is the frequency at the source, frequency of the source, of the sound source. If there was no motion at all, just nothing special was happening. Okay. And then there is this factor. It's V plus VO over V minus Vs. Let me try to tell you what all the symbols are here. Okay. Once you get this formula down, it's very simple. Okay. So V is the speed of sound. Okay. So plain old V is the speed of sound, the speed of the wave. VO is this velocity of the observer. And the reason I'm calling it velocity is because some cases I'm going to make it positive, some cases I'm going to make it negative. I'll tell you the convention very shortly. Okay? Whereas speed of sound will always be positive, but this velocity of the observer can be positive or negative. Vs is the velocity of the source. Okay, and then there's a very simple rule, and this is the very last thing I will tell you, is that VO and Vs are positive when they bring source and observer closer together. Okay, so the point is, okay, let me just draw 4 cases very quickly. It won't take me. This is source, this is observer. Source, observer. Source, observer. Source, observer. Okay, so let's suppose they both move towards each other. They're both moving closer to each other. Okay, so then I'd say the velocity of the source is positive, velocity of the observer is positive. Okay, they both are going towards each other. Everybody got that? Okay. Now let's suppose the source is moving away, but the observer is trying to go towards the source. So now the source is negative, but the observer is positive because the observer is trying to get together, the source doesn't want to get together. Okay, so then the observer, like this. So now the observer is negative, the source is positive, and then neither one of them wants to get close to each other, so Vs is negative and VO is negative. Does everybody get that? If you come closer, you're positive. If you go away, you're negative. That's the whole formula. Questions? All right, do you want to click in for clickers? Okay, yeah, since you came here, you probably do want to do that. So just click in for attendance. Once you've clicked in, go ahead and take off, and I'll see you guys tomorrow.